Imagine someday, as you gaze into the boundless starry sky, have you ever wondered what hidden mysteries it holds? Each of those distant lights, each star, like a ray of light piercing through the depths of time, tells us about events that have unfolded over billions of years. Try to picture how, in the absolute silence of cosmic space, celestial giants are born, illuminating entire galaxies with their radiance, and how their fading becomes the beginning for new life, a new cosmic cycle. What, in reality, happens to these stars over millions and millions of years, while we here on Earth merely watch their twinkling with admiration? Stars, in essence, hold the key to a deep understanding of the structure of the entire universe, its laws and its secrets. It is within the stellar depths, during complex thermonuclear reactions, that almost all the chemical elements that make up the planets, and of course ourselves, are created. The life cycle of each star is not just a sequential change of stages, but a truly captivating cosmic adventure, filled with dramatic events, grandeur, and enchanting beauty. Each star, like a living being, follows its own unique path, which, nevertheless, obeys certain patterns. Let us try to understand how stars are born, what the main stages of their life are, including periods of youth and maturity, and how they complete their life journey, leaving behind incredibly unique cosmic objects. We will learn how stars shape the chemical composition of the universe and how important their existence is for us, the inhabitants of planet Earth. Imagine yourself deep in space, at a vast distance from Earth. In this place, there is no sound. There is almost absolute darkness, but it is here, in this ringing silence, that amazing formations exist, known as nebulas. These giant clouds, consisting of gas and cosmic dust, can rightfully be called the cradles where new stars are born. It is in these nebulas that the life of a huge number of stars and entire star systems originates. For example, let us imagine one of the most famous and studied nebulas, the famous Eagle Nebula. It is located at a distance of approximately 6,500 light-years from us. This distance seems simply incredible, however. Despite this, the Eagle Nebula is clearly visible in images taken with powerful telescopes. In these images, it appears to us as giant, spread wings of an eagle, as if ready to take flight into the boundless expanses of space. The dimensions of the Eagle Nebula are truly impressive, about 30 light-years across. If we could see it with the naked eye, it would occupy a significant part of the celestial sphere. In the very heart of the Eagle Nebula, the process of star formation is continuously raging. It is in this giant cloud of gas and dust that a huge number of new stars are born. The Eagle Nebula is brightly lit by young and hot stars, many of which are many times greater in mass and temperature than our Sun. These young stars create a beautiful glow in the surrounding clouds of gas and dust, which shimmers with all the shades of the rainbow, from rich reds to delicate violets. This glow arises from the fact that the stars emit powerful ultraviolet radiation, which causes hydrogen atoms in the nebula to glow. Another nebula that invariably attracts the attention of astronomers and space enthusiasts is, of course, the Orion Nebula. It is located significantly closer to us, only 1,500 light-years from Earth. Active star formation processes also take place in its center, and under favorable conditions, it can even be observed with the naked eye. The Orion Nebula is one of the brightest and most noticeable places in the night sky. Inside the Orion Nebula is a huge number of young and hot stars, among which the star Theta Orionis stands out in particular, being one of the brightest and most massive stars known to science. In the Orion Nebula, you can see not only red shades, but also blue and even green. These diverse colors are due to the presence of various chemical elements in the nebula, such as oxygen and nitrogen. This amazing phenomenon is explained by the fact that different chemical elements emit light at different wavelengths when they are excited by high energy. Thus, when we look at the Orion Nebula, we see a complex picture consisting of many colorful spots of light, which create the impression of a bright cosmic fresco. But the largest and brightest nebula in our immediate cosmic environment is the Tarantula Nebula, which is located in the Large Magellanic Cloud galaxy at a distance of 160,000 light-years from us. This place can rightfully be called a real cosmic laboratory. It is here that stars are born that are thousands of times greater in mass and luminosity than our Sun. The Tarantula Nebula got its name due to its appearance, which resembles a giant spider with outstretched legs. These legs of the nebula are giant filaments of gas and dust that extend for 1,500 light-years. Inside this majestic nebula is a huge number of young and incredibly massive stars. Many of these stars are so hot that they emit an unimaginable amount of energy, heating the surrounding gas to temperatures of millions of degrees Celsius and creating a bright, breathtaking glow. The colors that can be observed in the Tarantula Nebula are even more saturated and vibrant than in other nebulas, with a predominance of rich blue and violet hues. These bright colors arise due to the ionization of oxygen and other chemical elements contained in the gas, which react to the powerful effects of ultraviolet radiation emanating from the stars. The Tarantula Nebula, in essence, is not just a visual miracle that you can admire endlessly. It is in fact a place where stars and future planetary systems can arise and actively develop. There are a huge number of stars in its territory, numbering in the thousands, and some of these stars are so massive that they are destined to live only a few million years, which by cosmic standards is an incredibly short period of time. These stars emit such a vast amount of energy that they are highly likely to eventually turn into supernovas, grandiose explosions that on the one hand destroy stars, but on the other hand create new chemical elements that can later become the basis for the formation of future planets, and possibly even life. Thus, each of these nebulas is not just a beautiful cloud floating in cosmic space. These are living, constantly changing parts of the universe in which new stars are born, and with each new birth, the future of our galaxy is created. These nebulas are real cosmic factories for the production of light and energy, which will exist for billions of years to come. And despite the fact that all these nebulas are located at vast distances from us, hundreds and thousands of light-years away, we still have the opportunity to see and carefully study them in order to try to understand how our universe is structured and how it will develop in the distant future. When we contemplate cosmic nebulas, they may seem calm and majestic, like huge clouds slowly floating through the vast expanses of space. However, these clouds are not just beautiful, they hide complex processes that lead to the formation of new stars and planets. One of the most important stages in this process is called gravitational collapse. This is the very moment when clouds of gas and dust begin to compress under the influence of their own gravity, gradually turning chaos into order and ultimately creating new stars. At the very beginning of their existence, nebulas look like huge, almost boundless clouds consisting of gas, in which hydrogen atoms and dust molecules move freely in the void, colliding with each other and constantly changing their position and speed. These molecules move completely chaotically, but all this time they obey an invisible force that permeates the entire universe: gravity. Gravity, in essence, is the force that acts between all objects that have mass. It is the foundation of all creation. If two objects have mass, mutual attraction inevitably arises between them. Even if these are relatively small objects, such as hydrogen atoms, their mutual attraction will be, although weak, but still existing. In the conditions of the emptiness of cosmic space, where practically no other forces act, gravity plays a crucial role. And when the density of gas or dust becomes slightly higher in a certain area of the nebula, gravity begins to act with greater force. Imagine you are flying through a huge gas cloud. All its particles move independently of each other, but one day, at some point in this cloud, A slight compression occurs, for example, due to the collision of several molecules or under the influence of an external factor, such as a supernova explosion, and the gas particles begin to compress in this place. Gravity in this place begins to increase, and the particles begin to attract each other, gradually forming denser areas. This can be compared to throwing a small pebble into water, and the waves emanating from the point where the stone fell gradually intensify. In this case, as the particles begin to gather together, with each step, the gravitational attraction between them becomes stronger, and they begin to accelerate toward the center. This is the beginning of gravitational collapse. In the initial stages, this process is very slow. The gas does not compress sharply, but gradually, and over millions of years begins to take the form of a dense fabric or cloud, which gradually compresses towards the center. In the very heart of this contracting cloud, pressure and temperature are steadily rising. Particles of gas and dust are constantly colliding, transferring energy to each other, and due to the ongoing compression, the temperature begins to increase even faster. As a result, the amount of gas grows, its density increases significantly, and the pressure inside the cloud reaches colossal levels. Imagine trying to squeeze an ordinary balloon. As you squeeze it, the air inside the balloon compresses, the temperature rises, and the balloon itself begins to heat up. In the case of a protostar, much the same thing happens. The more compressed the gas and dust particles are, the more energy is released in the form of heat. At the very center of the contracting cloud, the temperature can reach several million degrees Celsius. This process leads to the formation of a central hot region, which over time turns into a so-called protostar, an object that cannot yet be called a full-fledged star, but cannot simply be considered a cloud of gas either. It's a kind of baby star, which cannot yet shine as brightly as a mature star, but is already gradually gaining strength. The compression process continues to intensify relentlessly. When the temperature at the center of the cloud reaches a sufficiently high level, hydrogen atoms begin to stick together, forming heavier elements, and finally, the process of thermonuclear fusion is triggered. This is the very momentous occasion when a new star begins to shine for real. From this point on, the newborn star begins to emit light and heat, and the dark cloud of gas and dust, which was once vague and disordered, now turns into a glowing sphere, a star. This entire complex process, known as gravitational collapse, can last for millions of years, but something truly grandiose happens against its backdrop. Eventually, when the star is fully formed, it will become so bright that its energy will begin to actively affect the surrounding cloud of gas and dust, causing it to dissipate. The particles of gas and dust that remain after the birth of the star begin to move in different directions, and at some point, planets, asteroids, or even new stars may form from them in other parts of the cloud. Thus, gravitational collapse is not just a compression of gas, it is the beginning of a new cycle that leads to the creation of new worlds. This is a complex process in which nothing is lost, everything is transformed, and something completely new ultimately emerges. This process is fundamental to the creation not only of stars, but also of all planets, satellites, and perhaps even life. In this intricate dance of billions of particles, which are constantly colliding and attracting each other, one can see the immense power of gravity and its incredible influence on the structure of the entire universe. Thus, from emptiness and chaos, from a nebula, light appears. This is the very beginning of a star, the beginning of a new stage in the evolution of a celestial body. After gravitational collapse began at the center of a cloud of gas and dust, its particles compressed and a protostar appeared. This is an object that has not yet become a full-fledged star, but already possesses many of the characteristics that we have come to associate with stars, such as high temperature, density, and brightness, although much weaker than that of mature stars. A protostar is, in fact, a young star in the first stage of its development, which has not yet begun thermonuclear reactions, but is already actively preparing to launch them. From the moment of its birth, When a mass of gas and dust compressed into a single point, the protostar continues to actively accumulate matter. As with gravitational collapse, gravity continues to play a key role in this process. It attracts new particles, which causes the protostar to grow and increase in size. This process continues until conditions are reached at the center of the protostar, where the long-awaited thermonuclear fusion finally begins. However, even before the start of thermonuclear reactions, the protostar already exhibits some interesting features. For example, it begins to glow, albeit much weaker than a mature star. The luminosity of a protostar is due to the fact that the gas and dust compressing in its center release a large amount of energy, but this energy does not yet turn into light as it does in mature stars. All this happens exclusively due to gravitational compression. The energy released in this process heats the gas to several thousand degrees Celsius, which causes the protostar to emit light, mainly in the infrared region of the spectrum. Another important feature of a protostar is its temperature. At this stage, the temperature at the center of the protostar can reach several million degrees Celsius. However, in order to start full-fledged thermonuclear fusion, a process in which hydrogen turns into helium with the release of huge amounts of energy, the temperature at the center of the star must rise to at least 10 million degrees Celsius. At the same time, the surface of the protostar is not as hot as its center. The temperature of its outer shell can be around 3,000 to 4,000 degrees Celsius. This is still not enough to initiate thermonuclear fusion, but it is quite enough for the protostar to begin emitting light in the visible spectrum. This creates a kind of unstable equilibrium when the star continues to grow and accumulate mass, but its luminosity remains relatively weak. However, the energy released at the center of the protostar does not remain there forever. It gradually moves to its surface, and gas particles, rising, begin to cool. This creates a special circulation inside the protostar, known as convection. Under the influence of convection, hot gas particles rise to the upper layers and colder ones fall down, creating a peculiar cycle inside the protostar. Interestingly, during this period, so-called protoplanetary disks can form on the outer part of the protostar. These are clusters of gas and dust that rotate around the central protostar. These disks can be dense enough that planets, satellites, and other celestial bodies will begin to form from them in millions of years. In some cases, the disks are so large that they become sources for the formation of entire planetary systems, as in the case of our solar system cloud, which gave rise to planets, asteroids, and comets. But the most important thing is that throughout all this time, the protostar still does not emit its full luminosity. The forces of gravity continue to work steadily, and although the protostar already emits light and heat, the true radiance will begin only when the temperature in its center reaches the values necessary to start thermonuclear fusion. This can take millions of years, and only after that will the protostar turn into a real star, such as our Sun, emitting light for billions of years. At this stage, in the era of the protostar, its brightness can vary. It is not yet stable, and its luminosity may change periodically, as the star has not yet fully stabilized. These temporary fluctuations are associated with the ongoing processes of growth and absorption of gas. The active absorption of matter from the surrounding cloud of gas and dust is still taking place, which continues to have a significant impact on its further development. When thermonuclear reactions finally begin at the center of the protostar will stop growing and shrinking, and its internal pressure and temperature will reach values that will make it a full-fledged star. At this point, stabilization will begin in the center of the star, and the thermonuclear fusion of hydrogen into helium will provide the star with a long and relatively calm life, during which it will steadily emit light and heat. Thus, a protostar is not just the beginning of a star, but a real transitional stage that lasts millions of years. This is a complex process in which the star gradually gains strength and increases temperature, so that after some time it becomes a full-fledged source of light and energy for its entire planetary system. It continuously continues to grow, and each step brings it closer to becoming a full-fledged stellar system like our Sun, in the center of which thermonuclear fusion is continuously taking place. For most of its life, a star is in a kind of golden age, a stable and bright period that scientists call the main sequence. This is the time when a star reaches a fragile equilibrium between gravity, which steadily seeks to compress it, and the energy born in its depths, which seeks to tear it apart. This subtle but powerful struggle continues for billions of years, and it is this that turns the star into a true beacon of the universe. A real cosmic magic is played out at the very center of the star. Here, the temperature reaches a colossal 15 million degrees Celsius, and the pressure is so great that hydrogen atoms, which would never come close to each other under normal conditions, begin to merge, forming helium. This process, known as thermonuclear fusion, releases a huge amount of energy. Imagine, every second our Sun burns millions of tons of hydrogen, and all of this turns into light and heat that we feel on Earth. The energy born in the core begins its long and winding journey to the surface of the star. But this is by no means an easy walk. Inside the star, light constantly collides with gas atoms, bounces off them, and changes direction again. This chaotic dance of photons can last thousands and sometimes millions of years before the light manages to break through. When energy finally reaches the outer layers of the star, it transitions into a zone where huge masses of plasma begin to actively mix. Imagine gigantic flows of hot gas that rise up, then gradually cool down and plunge down again like an eternal, boiling ocean. Amazing wonders occur on the surface of the star, which we call the photosphere. The photosphere may seem smooth and bright, but if we could get closer to it, we would see the so-called granulation, millions of tiny cells, similar to sunspots, each of which is comparable in size to a large city. The temperature on the surface of a star varies depending on its mass. For our Sun, it hovers around 5,500 degrees Celsius, but for massive blue giants, it can soar to 30,000 degrees Celsius. The Sun is our nearest star, and it serves as an excellent example of how main sequence stars operate. By studying it, we can unravel the processes that unfold in any star of this type, from its very birth to the moment it exhausts its fuel reserves. Let's delve into a detailed exploration of how the Sun functions at various levels. After energy, in the form of photons, escapes the core, it must traverse several layers before reaching the surface. Within the Sun, two primary zones are distinguished, the radiation zone and the convection zone. In the radiation zone, energy travels in the form of photons, but the path these photons take is incredibly long and winding. Solar photons, born in the very heart of the Sun, constantly collide with atoms in this layer, altering their direction of travel. These collisions cause a photon to potentially begin moving in an entirely different direction, and its path becomes utterly random. Consequently, the energy leaving the core can meander through the radiation zone for millions of years before it reaches the higher layers. This zone constitutes roughly 70% of the Sun's total radius. When energy reaches the upper layers, it enters the convection zone. This is a region where vigorous mixing of matter occurs. Hot masses of gas rise upward, while cooled masses sink downward. This circulation of matter resembles water boiling in a pot. The movement of hot gases carries energy to the Sun's surface, creating granulation, tiny bubbles on the photosphere, which we can observe in photographs of the Sun taken with telescopes. When energy reaches the photosphere, the visible surface of the Sun, it is radiated into the surrounding space. The Sun's photosphere is the layer where light becomes visible to us. The temperature of the photosphere is approximately 5,500 degrees Celsius. This is precisely the temperature at which the Sun begins to emit visible light. The surface of the Sun is not smooth, but is covered with granules, bubbles of hot plasma that continuously rise and cool. These granules can reach several thousand kilometers in diameter, and their constant movement creates a characteristic structure, which we see as a distinctive texture in photographs of the Sun. Granules have a very high temperature, around 6,000 degrees Celsius, and they float on a colder shell, the temperature of which is about 4,500 degrees Celsius. No less crucial to the Sun's functioning is its powerful magnetic field. Within the Sun, the continuous movement of conducting plasma particles creates complex magnetic fluxes. This magnetic field governs many phenomena that we observe on the Sun's surface, including sunspots, solar flares, and coronal mass ejections. Sunspots are areas of the photosphere where the magnetic field disrupts the normal process of convection, leading to a decrease in temperature. These spots appear darker because they are cooler than the rest of the Sun's surface. In the area of sunspots, the temperature can be several thousand degrees lower than in the surrounding regions. Solar flares are powerful bursts of energy that occur due to abrupt rearrangements and changes in the Sun's magnetic field. These flares can eject tremendous amounts of plasma and magnetic energy into space, and they can impact radio communications and navigation systems on Earth. Furthermore, solar flares can also disrupt the normal operation of Earth's artificial satellites. Coronal mass ejections, on the other hand, are even more powerful and massive ejections that hurl enormous clouds of plasma consisting of electrons and ions into space. These ejections can reach billions of tons of matter and accelerate to speeds approaching the speed of light. They can reach Earth and cause spectacular phenomena such as auroras. The Sun's luminosity, that is, the amount of energy it emits per unit of time, is colossal energy, and it is the result of thermonuclear reactions that continuously occur in the very heart of the Sun. By measuring the Sun's luminosity, scientists can calculate its mass and other important parameters. The Sun's temperature in the photosphere, as already mentioned, is about 5,500 degrees Celsius. However, the temperature in its corona, the outermost region of the Sun's atmosphere, can reach several million degrees Celsius. This phenomenon, where the outer part of a star is significantly hotter than its surface, remains one of the unsolved mysteries of astrophysics. One leading theory suggests that the high temperature of the corona may be related to magnetism. The Sun's magnetic fields can transport energy from its inner layers, effectively heating the corona. The Sun has been on the main sequence for about 4.5 billion years and will continue its stable path for roughly another 5 billion years. During this time, it continuously burns hydrogen, converting it into helium, and emits a huge amount of energy, sustaining life on Earth. However, sooner or later, the Sun will exhaust its hydrogen reserves. When this happens, it will begin to transform into a red giant, and its size will increase significantly, engulfing the nearest planets, including Mercury and Venus. This process is the inevitable end of a star's life on the main sequence. However, despite the inevitability of its aging, the Sun continues to support life on Earth, providing us with light and heat, and it is a crucial part of the solar system. With its help, we understand how stars work, and we can explore other stars in our galaxy, comparing their life cycles with the life of our Sun. Having completed our study of the life of our Sun, let's turn our attention to how it fits into the broader context of the universe among other stars. After all, the Sun is far from the only star that exists in our galaxy. Stars come in various types, and each type has its own characteristics, which are determined by its mass, temperature, and other important attributes. In this section, we will take a closer look at the types of stars that can be found in our galaxy, from giant, hot blue stars to more serene but numerous red dwarfs. Let's consider their sizes, luminosity, behavior, and even how they become part of the cosmic cycle of life. One of the most impressive types of stars is giants and supergiants. These stars can be tens or even hundreds of times larger in size than our Sun. Despite their enormous mass and size, they have a much shorter lifespan. An example of such a star is Aldebaran, a red giant in the constellation Taurus. If Aldebaran were in the place of our Sun, its outer layers would encompass the orbit of Earth, and its luminosity would be 1,000 times brighter than that of our Sun. The temperature of its surface is about 4,000 degrees Celsius, which is significantly lower than the temperature of the Sun, and that is why it emits light in the red part of the spectrum. But among the giants, there are not only red stars, there is also an entire class of stars known as blue giants, which, despite their impressive size, have a much higher temperature and luminosity. These stars can be 50 times more massive than our Sun. The brightness of such stars is tens of thousands of times greater than the luminosity of the Sun, and their temperature can reach from 20 to 30,000 degrees Celsius. They are incredibly hot and emit light predominantly in the blue part of the spectrum. However, despite their dazzling brightness, blue giants are stars with a very short life cycle. Due to the extremely rapid consumption of their nuclear fuel, they live only a few million years, which is an insignificantly short period for stars. Blue stars, or blue giants, are among the brightest and hottest stars that can be found in our universe. These stars have a mass that exceeds the mass of the Sun from 10 to 50 times. The temperature of their surface can reach from 20 to 30,000 degrees Celsius, which is several times higher than the temperature of the surface of our Sun. Due to their extremely high temperature, blue stars emit light predominantly in the blue part of the spectrum, which significantly distinguishes them from other types of stars, such as our Sun, which emits light with a yellowish tint. One striking example of blue giants is the star Regulus, located in the constellation Leo. It is the brightest star in this constellation and is many times brighter than our Sun. Blue giants typically have a very short life cycle, and their life can last only a few million years. This is because blue stars consume their nuclear fuel much faster than less massive stars. When giant and supergiant stars exhaust their reserves of nuclear fuel, they begin to expand and eventually turn into red giants. At the very end of their life, these stars explode as magnificent supernovas, after which they leave behind neutron stars or even black holes. One of the most common types of stars in our galaxy is red dwarfs. These stars are so numerous that they make up approximately 70% of the total number of stars in our galaxy. Red dwarfs are stars with a mass from 1/10 to 1/50th of the Sun's mass and a luminosity several hundred times weaker. The temperature of their surface is from 3,000 to 4,000 degrees Celsius, which makes them red and dim. Despite this, red dwarfs are incredibly important for science, as their life cycles can last trillions of years, which is far longer than the lives of more massive stars. Due to their low luminosity, red dwarfs are difficult to see with the naked eye. They don't radiate bright light, but thanks to their longevity, they exist much longer than larger and brighter stars. Some of them can live up to 100 trillion years, which is much longer than our solar system has existed, and stars like our Sun. One of the most prominent examples of a red dwarf is Proxima Centauri, the closest star to us after the Sun. It is only 4.5 light years away from us, but despite its proximity, its light is too faint to be seen with the naked eye. The size and luminosity of a star are directly related to its mass. These are important parameters that determine how a star will evolve in the future. For example, stars with a mass greater than 8 times the mass of the Sun turn into supernovae at the end of their lives, while less massive stars tend to end their lives as white dwarfs. The luminosity of a star depends on its temperature and size. More massive stars, such as giants and supergiants, emit much more light than stars of lower mass. This is because such stars have higher temperatures and wider outer envelopes. Stars like our Sun live an average lifespan of about 10 billion years. However, stars that are much more massive than the Sun live much shorter lives, only a few million years. Lower mass stars, on the other hand, can live significantly longer, even trillions of years. Now that we've looked at the lives of stars and their types, let's take a look into the very heart of a star, at the process that actually allows a star to exist and shine. We are talking about nuclear fusion, which is that magical process by which stars emit light and heat. Nuclear fusion is the process by which atomic nuclei merge to form heavier elements, releasing a tremendous amount of energy in the process. This is exactly what happens in the depths of stars. At the center of a young star, such as our Sun, the main fusion reaction is the conversion of hydrogen into helium. These reactions take place in the so-called proton-proton cycle, in which hydrogen nuclei, or protons, collide with each other, overcoming electrical repulsion thanks to the colossal pressure and temperature at the center of the star. During this process, two protons fuse to form a deuteron, a nuclear isotope of hydrogen with one proton and one neutron. The deuteron then captures another proton, forming an isotope of helium. Eventually, two helium isotopes fuse to form stable helium and release two protons. This reaction releases a tremendous amount of energy in the form of photons, which propagate outward, and this heat and light we feel as the star's luminosity. However, as powerful as the conversion of hydrogen to helium is, it cannot last forever. Gradually, the hydrogen in the center of the star runs out, and the process of synthesizing heavier elements begins, starting with carbon, nitrogen, and oxygen. When a star exhausts the hydrogen in its core, it begins to contract under its own gravity, and the temperature in the center begins to rise. When the temperature reaches about 100 million degrees Celsius, the process of synthesizing carbon and oxygen begins as part of the so-called carbon-nitrogen cycle. In this process, carbon, nitrogen, and oxygen act as catalysts for the synthesis of hydrogen into helium. Unlike the proton-proton cycle, this process requires much higher temperatures and is performed primarily in stars more massive than our Sun. As a star's mass increases, it begins to transition to the synthesis of even heavier elements. For stars with a mass greater than about 8 times the mass of the Sun, reactions synthesizing carbon, neon, magnesium, and oxygen begin to activate. These are more complex reactions that occur at temperatures of around 500 million degrees Celsius. It is in these stars that elements such as silicon, sulfur, and other heavier elements arise, which also fuse in the process of thermonuclear reactions. Stars with such high temperatures and pressures can synthesize elements that form the basis of the entire earthly world, such as iron and nickel. But the synthesis process does not end there. However, despite the fact that stars can create heavier and heavier elements, the process of iron synthesis in a star has its own peculiarity. When the temperature and pressure in a star become high enough to synthesize iron, which is about 2 billion degrees Celsius, the synthesis reactions begin to behave differently. Iron and nickel are elements that have the most stable nuclear structure. The energy that is released during the formation of iron is significantly less than during the synthesis of lighter elements. Stars whose mass is several times greater than the mass of the Sun can no longer support thermonuclear reactions after the synthesis of iron. This leads to a chain reaction of destruction in the star. Iron accumulates in its center, and at some point, this leads to a catastrophic supernova explosion. At the moment of a supernova explosion, the temperature in the star can reach trillions of degrees Celsius, and then such super-heavy elements as gold, platinum, and uranium are synthesized. This is a complex process that ultimately enriches cosmic space with heavy elements from which new stars, planets, and possibly even life are then formed. Now let's look at the final act of a star's life, which is full of grandeur and beauty, despite the fact that the star is already at the twilight of its life. When a star like our Sun approaches the end of its life, Its end will not be as dramatic and powerful as that of more massive stars, which end their lives with colossal supernova explosions. On the contrary, small stars fade into oblivion quietly but beautifully. Instead of bright flashes and destructive cataclysms, they become sources of amazing cosmic objects that will shine for a long time, leaving behind unimaginable beauty. When a star exhausts its nuclear fuel, thermonuclear reactions cease to occur in its center. In the case of a small or medium-sized star, its core begins to shrink and its outer layers expand. When the hydrogen in its core is exhausted, the star begins to experience a period in which it gradually loses its outer layers, ejecting them into cosmic space. This process is accompanied by the emission of bright and colorful clouds of gas, forming the so-called planetary nebula. Don't worry, stars don't turn into planets, despite the name. A planetary nebula is a bright cloud of gas and dust that glows when its central star continues to shine. The nebula itself can have a variety of shapes and colors, from bright greens and reds to purples and even blues. These colors depend on what chemical elements are present in the ejected gas. For example, red appears when hydrogen is present in the nebula, and green when it contains oxygen. Planetary nebulae are not only bright, but also mysterious objects. They often have the shape of a bubble or ring, which gives them a truly cosmic and unearthly appearance. And their discovery became possible only in the 19th century, when astronomers began to observe that some stars at certain stages of their lives begin to surround themselves with such gaseous envelopes. And although the name planetary can be confusing, it is not related to planets in any way. Rather, it reflects the shape of the nebula, which in the early stages of observation remotely resembled planets seen through a telescope to astronomers. But the most amazing thing begins after the outer layers of the star leave it. In the very center remains the core, which no longer supports thermonuclear reactions. This core, having survived so many changes and passed through many cycles of thermonuclear reactions, becomes a white dwarf. A white dwarf is a star that no longer burns as brightly as it used to. All of its thermonuclear reactions cease, and its internal gravitational forces begin to compress, but not so much that an explosion occurs. The temperature of a white dwarf can reach tens of thousands of degrees Celsius, but despite this, the star no longer emits light as in its youth. It gradually cools down, and its luminosity decreases. But a white dwarf remains one of the most stable objects in the universe. It will slowly dim and cool for billions of years until it turns into a black dwarf, a star that no longer emits light, and its temperature approaches absolute zero. This may seem a little sad, but there is something majestic about this process. White dwarfs are deceased stars that quietly but surely follow their destined fate. They maintain their presence in space, remaining virtually invisible to the naked eye. But at some point, if we could observe them long enough, a white dwarf would become a cosmic monument, reminding us of its stellar past. And so, even when a star leaves quietly, it still leaves behind incredible traces. Planetary nebulae, surrounded by gases and dust, continue to shine with bright colors as a reminder of its past greatness. And white dwarfs, which were once blazing stars, become mysterious cosmic obelisks receding into eternity. They leave quietly, but beautifully. These are not just beautiful words, but a real description of how stars complete their life cycles, leaving behind traces that will exist for a long time, reminding everyone of their short but bright existence in the vast expanse of the universe. When a massive star approaches the finale of its life, its fate turns into a majestic and dramatic spectacle that unfolds on the vast cosmic arena. The explosion of a supernova is an event of incredible force, but its outcome is not always the same. What remains after a star explodes depends directly on its mass. It is mass that determines whether a star will become an enigmatic neutron star or fade into darkness, transforming into a black hole. But let's delve into how all of this works. It all begins with a massive star, much larger than our Sun, at least 8 or 10 times more massive, exhausting the nuclear fuel in its core. Throughout its life, the star has burned, synthesizing elements from hydrogen and helium. But at the end of its life, the temperature within its core becomes so high that heavier and heavier elements begin to form: carbon, oxygen, silicon, and finally, iron. Iron becomes the turning point in the life of a star. It is an element that does not release energy during synthesis. On the contrary, it actively absorbs it. When the core of a star fills with iron, it is no longer able to resist its own gravity. A rapid collapse or compression begins. The star's core implodes in fractions of a second, the temperature soars to tens of billions of degrees, and gravitational forces become simply overwhelming. If the mass of the core does not exceed a critical limit, approximately 1.5 times the mass of the Sun, known as the Chandrasekhar limit, it stops its compression due to the degenerate pressure of neutrons. This is how a neutron star is born. But if the mass of the core exceeds this limit by 2 or 3 solar masses, the neutrons can no longer withstand the colossal pressure of gravity. In this case, the core continues to compress, and the star ultimately transforms into a black hole. Let's take a look at what a neutron star is like. It's a tiny but incredibly dense object. To imagine its density, think about this. 1 teaspoon of neutron star material would weigh as much as a mountain range, that is, on the order of 10 billion tons. With a diameter of only about 12 miles, such stars are more compact than many cities on Earth. Within this small cosmic sphere, neutrons, the particles that make up the nuclei of atoms, are densely packed, as if in an incredibly dense crowd where no one can move. They are held together by what is known as the degenerate pressure of neutrons, which prevents further collapse of the star. It is a unique physical phenomenon, one of the most amazing aspects of quantum mechanics, making neutron stars possible in principle. But neutron stars are striking not only for their incredible density. They have one of the strongest magnetic fields in the universe, which can be billions of times more powerful than the Earth's magnetic field. These powerful magnetic forces give rise to unusual and interesting phenomena. For example, some neutron stars become pulsars. These stars rotate at incredible speeds, emitting powerful beams of radio emission into space. When such a beam passes through Earth, we see it as a regular pulse of light, like the flashing of a beacon in the night. Sometimes the magnetic field of a neutron star is so powerful that it turns it into a magnetar. These rare objects can produce catastrophic bursts of energy, comparable to the most powerful explosions that exist in the universe. However, if the mass of the stellar core exceeds 3 solar masses, no forces can restrain its collapse any longer. It continues to compress until a black hole forms, an object whose gravity is so strong that not even light can escape its pull. All the star's matter collapses into a tiny point called a singularity. This is a place where density becomes infinite, and the laws of physics as we know them cease to work. Black holes are the most mysterious and amazing objects in the universe. Their name inspires awe, and their nature remains one of the most fascinating mysteries for scientists. Imagine a place where gravity becomes so strong that nothing, not even light, can escape. That's a black hole, the offspring of a massive star's death and one of the most powerful forces in space. When a star with a mass exceeding 20 to 30 times the mass of the Sun exhausts its fuel for thermonuclear fusion, its core becomes unstable. Gravity, which was previously balanced by the powerful pressure of radiation, begins to win. The core collapses, imploding into a point of incredibly small size called a singularity. At this point, density becomes infinite, and the familiar laws of physics cease to apply. It's a place outside of time and space, where the concepts of before and after simply lose all meaning. A black hole is surrounded by an event horizon, an invisible boundary through which nothing can return. It's like a waterfall in a river. You can swim up to a certain point, but once you cross the boundary, you can no longer avoid falling. The event horizon of a black hole is that waterfall where gravity becomes all-consuming. The size of the event horizon depends directly on the mass of the black hole. For a stellar black hole formed from a massive star, the radius of the event horizon may be only a few miles. However, for supermassive black holes located in the centers of galaxies, this radius can reach millions or even billions of miles. For example, the radius of the event horizon of the black hole at the center of our galaxy, Sagittarius A, is about 17 solar radii, and its mass exceeds 4 million solar masses. But a black hole is not just emptiness. An accretion disk of absorbed matter often forms around it. This is a disk of gas, dust, stellar debris, and even entire stars that have strayed too close to the black hole. This matter heats up to extreme temperatures, reaching millions of degrees Celsius, and begins to emit powerful streams of light and X-rays. It is thanks to this radiation that scientists can see black holes, even though they themselves remain invisible. If matter from the accretion disk falls onto the black hole unevenly, jets can arise, powerful streams of plasma ejected from the poles of the black hole at speeds close to the speed of light. These jets can pierce intergalactic space for millions of light years, becoming distinctive beacons for astronomers. Black holes come in different types. Stellar black holes form from stars, and their mass can range from a few to dozens of solar masses. Intermediate black holes, with masses of hundreds or thousands of suns, are less common, but they likely play an important role in the formation of larger objects. Finally, supermassive black holes, located in the centers of most galaxies, have masses millions or billions of times greater than that of the Sun. For example, at the center of galaxy Messier 87 lies one of the most massive known black holes, with a mass reaching 6.5 billion times that of the Sun. An interesting fact: black holes are not cosmic vacuum cleaners at all, as many think. If the Sun were to magically transform into a black hole with the same mass, Earth would continue to orbit it as before. However, for objects that get too close, its gravitational power becomes catastrophic. Black holes also play a key role in the formation of the universe. They help shape galaxies, regulate star formation, and participate in the redistribution of energy and matter. Their gravitational waves, caused by the merging of black holes, have already been detected by scientists and give us a new way to hear the universe. And although these objects seem like an absolute end, they are the beginning of something entirely new. Matter absorbed by a black hole does not disappear without a trace, but becomes part of a grand cosmic cycle, possibly influencing the formation of future stars and galaxies. Black holes are true cosmic alchemists, rewriting the laws of nature as we know them and continuing to inspire scientists to new discoveries. So, our stellar odyssey is coming to its logical conclusion. We have come a long way from the birth of stars in dense gas and dust nebulae to their majestic completion, be it the quiet departure of a white dwarf, the dazzling flash of a supernova, or the formation of an enigmatic black hole. Each star is a small universe that carries the story of its life and has a significant impact on the cosmic space around it. Stars are not just distant lights twinkling in the night sky. They are generous sources of light and heat, creators of the elements that make up absolutely everything around us, including ourselves. Every drop of iron in our blood, every atom of calcium in our bones, is, in essence, a gift from distant stars that completed their life cycle billions of years ago. And although it may seem to us that stars are eternal, their life, like ours, is limited in time. But it is in this limitation that their true greatness lies. They transform their energy, their light, into creation, making the universe the way we know and love it. So, the next time you look at the night sky, remember that it is not just a mesmerizing cosmic spectacle. It is a vast book written by billions of stars, And each page of this book holds the secret of the birth, life, and death of these distant luminaries. And perhaps somewhere out there, in the vast expanses of space, a new star is being born right now, which will one day illuminate our path.